That's a better size. So, lab exercise 7, thermal response. So in this lab, we will estimate the lumped parameter thermal resistance and capacitance of a 3D printed block of PLA by measuring its temperature time response to interval heating via a resistor. Temperature measurements will be made with thermistors connected to Wheatstone bridge circuits, the output voltages of which will be measured with a MyRio device. A calibration curve for each thermistor will be generated. So there's sort of a lot of steps here, okay? So you gotta follow them very closely, otherwise you're gonna get lost. We will be inferring the lumped parameter thermal resistance R and thermal capacitance C of a block of PLA from its time response. Each block has a 56 ohm, actually one of them's got like a 47 ohm resistor embedded within, acting as a heater, and 3 thermistors embedded, but we will only be using the one closest to the resistor to measure the temperature response of the block. So hopefully you guys have been introduced to the concept of a thermistor, but I'll just mention it for just a moment. A thermistor is a resistor that is very temperature dependent. Okay, so I've mentioned previously that all resistors are temperature dependent, but thermistors are specifically designed to be temperature dependent, whereas other resistors are hopefully not as much so. So these thermistors can be used if they're temperature dependent. That means that their resistance changes with temperature, and if we are to calibrate them, which is to say if we're to measure a given temperature and a corresponding resistance associated with that resistor, then we can infer from the resistance at a given time what its temperature must be. And so that's what we're going to do. In this lab, we'll use the thermistor as a sensor for the temperature measurement of a block of PLA, and the PLA is just a type of plastic, and it's what the 3D printers in it's most, I would say, base level 3D printers mainly print in PLA. It's a nice material, and fortunately we shouldn't be melting it in this application. So nothing else major there in the intro. Wheatstone bridge circuit, you may have been introduced to in the past. We'll look at it a little bit and discuss it in a few minutes. So you're going to start off and you're going to do thermistor calibration. So we're not going to do a full calibration of our thermistor. We need to calibrate these thermistors by measuring their resistances at a measured room temperature. We say calibrate in quotes because we're not fully calibrating the thermistors ourselves, but partially relying on the manufacturer's datasheet. We will develop a calibration curve and a lookup table for each thermistor. Well, actually, so each group will be doing just one thermistor. So there are 3 in each block, or except for one of the blocks just has one. But each group is only going to use the one thermistor that's closest to the resistor. So I initially, when I designed these, I was being a little bit more ambitious and having 3 thermistor measurements, but let's just say that didn't go well. So just do one now. Okay. I was a little ambitious with that. Thermistors are highly temperature-dependent resistors. Calibration curves of many thermistors, including those we will use, can be described by the Steinhart-Hart equation. It's not redundant. The following Vichy datasheet gives the equation's parameters based on an R25 resistance, which means the measured resistance of the thermistor at a temperature of 25 C. However, we don't have, so this is the data sheet. you are going to want to look at that. So go ahead and click the link. However, we don't have a climate-controlled environment at 25C, so this isn't helpful. Okay, so if we had that, we could just measure the resistance of the thermistor at 25C, and then we'd be off to the races. But since we don't have a temperature-controlled environment to keep it at 25C for a resistance measurement, instead we'll use this other method. So conveniently, the manufacturer provides the following spreadsheet that can be used to calibrate our thermistors at non-25C temperatures. So that is an Excel file. So go ahead and download it, and it's pretty straightforward to use, but I'll sort of walk you through. So our thermistors have nominal resistance of 25C at R25 equals 10K. So let's see. Oh yeah, I can't do that. Whoa. That wasn't what I was trying to do. I'm actually going to pull it up. I wasn't going to, but doing it now. Resources, CC6400, C1.XLS. I think. Yeah. I've already downloaded it. I didn't really have to do that. Now I'm going to open up JVXL here. What are we doing? JVXL, where are you? It's taking a minute. Okay. Yeah, so here we are. So somebody thought this thing through. It's pretty involved. There are different tabs, though. Even in JVXL, you can see this. So this is the tab we need, the RT coefficient tab. So you want to go here, and we're mainly going to be entering in stuff in the blue boxes. Now we're going to be selecting our calibration curve out from down here. So instead of having to measure the whole calibration curve, we're going to do one measurement, which will effectively give us the entire calibration curve, which is not as good as doing a calibration ourselves, but it's still pretty good. So, and I'll tell you what, it's a lot easier. So there's that. Okay. So as the temperature increases from there, so at 25C, the resistance is 10K. As the temperature increases from there, the resistance decreases, so it'll get below 10K. This means we have a negative temperature coefficient, or NTC thermistors. So that's a sort of a buzzword for the type of thermistor, which just means as the temperature increases, the resistance decreases. That's all negative temperature coefficient thermistor means. The spreadsheet gives a temperature resistance relation. Okay, so we'll look back at the spreadsheet here, and we've got temperature in Kelvin, right? Let's go back to here. We've got temperature. Actually, this is in Celsius. Temperature in Celsius, and we've got a resistance here, which is in kiloohms, I believe. Is it in? Oh, that's a ratio. Resistance, they're in ohms. So 40,000. As you increase, so around 25C, we would expect to see somewhere around 10K. So this one is not calibrated to the same value, though. So the reference temperature here is 20.5, not 25C. Okay, so let's go back to our notes here. So additionally, it gives an estimated temperature deviation, delta T, for each point on the curve. So this thing's going to give us, once we actually plot it, it's going to give us a curve that looks like for a given resistance that we want to look up, we can look up at temperature, and it was a negative temperature coefficient resistor. So as you increase the temperature, you decrease the resistance, and as you increase the resistance, you decrease the temperature as you will, if you will, something like that. So it's non-linear, but however this looks, I don't even remember what the non-linearity looks like. It's probably good I'm not showing you too, so then you got to find out for yourselves. So it's not just going to give us temperature versus resistance. It's also going to give us temperature deviation values. It's going to give us like error bar values here, delta T. Okay, so that's important. We're going to want to use those because we're getting a little bit more precise with our measurements. Now we're going to want to start to talk about what is the like uncertainty associated with a given value. So you guys are getting towards the end of your term here, so you gotta start doing things like that, a little bit more pro-like. So it counts for the tolerance of our temperature measurement. So calibration measurements. The following procedure will yield the required measurements. So you gotta get a temperature measurement device. So there are a lot around. So get one and write down what model you're using. Okay, there are a lot of different types. There's like an infrared one. There are probe-based ones. There are there's like, I don't know. There are a lot of different types. So I don't care which one you use, just as long as you can note down the model so that you can look up what its tolerance accuracy is, because we want those delta T values. So then connect the PLA block to the breadboard. So go through this in detail because it's telling you like little details of how to connect things so that it doesn't mess up. You're gonna take a baseline measurement of the resistance of the load resistor. So this is the heater resistor of 56 ohms. Remember, one of them is like 47. It doesn't really matter though, because you're gonna measure it anyways, and you're gonna write it in right here. And then you're gonna measure what the resistance of the thermistor is, and you're gonna write it here, and you're gonna measure the temperature of the block before you start heating it up, or of the air around, depending on what your temperature setup looks like. Temperature measurement setup. Okay, generate the thermistor calibration curve. So the following procedure will yield the required calibration curve. Go through use the spreadsheet. We're going to use these three measurements that were just made, put them into the spreadsheet along with a couple other values that I tell you about. So go ahead and go through this in detail. I don't write it for myself. I actually write it for you guys. I know, it's shocking. Great. So notice what I'm doing here. So I'm having you guys do this like online. So there's Excel on those computers, on the lab stations. There's also MATLAB. So I'm having you guys get the calibration curve in Excel and then bring it over into MATLAB. And when you have it in MATLAB, you're gonna plot it. You're gonna plot your calibration curve. And I explain even like the details of how to do that, the functions that you're going to want to use for that. Take care to make sure that this is right, because everything else is going to depend on it. So make sure that you are careful with how you bring the data in and that it's looking good on your plot. Okay, build the circuit. The Wheatstone bridge circuit we are building can be represented by the diagram of figure 7.1. So here's the Wheatstone bridge, and notice there's a voltage source, okay, and it goes across this bridge of 4 resistors. We encountered a bridge in a previous lab. It was a diode bridge. The resistor bridge is a lot less complicated, and you've probably encountered it, but doing a circuit analysis on this is pretty straightforward because it's just 4 resistors, so I'm going to leave that for you guys to do an exercise to do the circuit analysis. So you want to know what the output voltage is here, given an input voltage Vs. Now, I'm going to caution you because Wheatstone bridges are common circuits, and so if you just Google Wheatstone bridges, you'll see circuit analysis. I mean, Wikipedia's got it. Everybody's got it. Oh man, I'm refraining from political jokes right now. You're welcome. Okay, so if you use those analyses from the online sources, it's totally fine, I don't care. But just be cautious with the naming of the resistors. And also be cautious because we're not going to be balancing our bridge. So you can balance the bridge, which is to make the output voltage 0 if the resistor ratios are equal. Which is one way to do a measurement of using a Wheatstone bridge. But the other way is to actually measure what the output voltage is and have an unbalanced bridge. And that's the approach we're going to use. The main reason that we're using that is that our measurements are going to be pretty much, well, they're not super fast, but they're dynamic. And when you do a dynamic response, you don't always, you have to adjust your bridge to balance it. And if you want to balance your bridge as the thermistor resistance is changing, you're going to end up with you have to balance it faster, much faster than the system's changing and the temperature's changing, which is fine. And actually, that's how I used to do it. That we have these digital potentiometers in the cabinets, and you can do that. But I think it's more complicated, and there's not really any good reason to do it. So we'll just do the unbalanced bridge instead. Notice that we're going to be measuring the output voltage of the bridge into the C connector. So you can use in zero minus and plus, so that's fine. Or you can use 3 is the ground, 5, 7, and 6 for this ground. So you have some options. It's not really a big deal which one you use. If you go through the instructions, it kind of gives you a little bit of detail about which ones you can use and which ones are better. But it's not a big deal. You can use any of the analog inputs for your measurement. Great. Then build a LabVIEW program to control the MyRio to save and capture the data. You can pretty much just copy one of your previous dynamic response VIs from before and adapt it slightly. The main thing you're going to want to adapt is that your timed loop has the timing controlled by this little box up here. One of the parameters in this box is DT. Sweat here. This flannel's a little warm. Is DT. And DT is the amount of time between loops, right? Amount of time for each loop to execute. So that controls your sample rate. We don't need a blazing fast sample rate in this one. So I think in a lot of the previous labs we did like 1 or 10 milliseconds for our DT. This thing is in milliseconds. It's good to remember. we probably only need to be at about half a hertz. Okay, so dt would be 500 milliseconds, right? If I know math. Okay. Once the response has reached something close to steady state, disconnect the power supply. So this is okay. So we're going through the loop. We're capturing the data. Essentially, what we're doing is we're starting the measurement of the temperature before we connect up the power supply to power the heating resistor. We're gonna start taking data, and then we're gonna connect the heating resistor, and then the temperature is gonna go from room temperature, like 25 C or whatever, and then it's gonna do this sort of exponential decay up, okay, because it's heating. So while that heating process is happening, you have to, or you're going to see the temperature increase. It'll look like a decaying exponential, and then you're going to, once it's reached a steady state, or pretty good, it's not really changing much, it's like pretty flat, then go ahead and keep measuring, and then disconnect, and you're going to get the temperature drop back to room temperature over time. So it's going to be 2 exponentials, and then stop it once it gets pretty much to this point where it's flat. If you take too much extra data, you have to kind of slice it off, otherwise it messes up some of your data processing tools later on, because we're going to do a linear regression using a logarithmic plot, and so if you have a bunch of flat stuff out here, it kind of fucks that up, bleeps that up, is what I said. Okay. Good. So I went ahead and did the analysis for you. So the thermal side of this is a dynamic system as well. We're going to learn how next semester in the system dynamics class how to do the analysis on thermal systems. But for now, I did it for you. So in the report requirements, there's this nice little handout here, the thermal lab handout. Definitely gonna want to check that out. I bet I downloaded that. Where am I? Resources. And there we go. Boom. So you're gonna want to check this out. Look, I did a linear graph. You can do linear graphs for thermal systems, not surprisingly. And I do the analysis. It's pretty simple. It's a first order system, and I solve the differential equation even for you, and I show you what the response is going to look like, and I give you a theoretical prediction of what that should look like. Okay, and then I show you how to do the estimation. Okay, so the idea is we're going to measure, so the lumped parameter elements that we use to model the thermal system. So even though we haven't done this yet, it's not surprising that you can think of a thermal system as being kind of like an electronic system, right? Where we have a resistor and a capacitance, where we have thermal energy stored in the capacitance, the thermal capacitance, and then thermal energy that flows through resistances. So it impedes the flow of heat. So this is the dynamic model that we're using, and we want to estimate what the thermal resistances are and what the thermal capacitances C from the data that we just took. So this is actually a pretty useful thing to be able to do. I first derived this model, which isn't super complicated, but I first derived it when I was working on this smart thermostat project with Puget Sound Energy, and like it's like super useful to be able to do this. So you get to measure a couple temperature responses. So measure the heating phase, the heating interval, right here, and so we'll call it interval 1, the heating interval, and then also measure the decay interval. And if you measure both of those intervals, you can actually estimate both parameters, R and C. And I essentially do all of that work for you. I show you how to estimate R and what to plot and what slopes are going to give you which parameters. I do it all for you because it's actually a little bit complicated. The first year I gave this, I did not give people this, and it wasn't successful. So now I give you the analysis part. So you have to understand it though. So go through this and try to engage in it, even though you don't necessarily understand every aspect of it. You should kind of get what's going on. You can see a lot of familiar things here: primary variables, secondary variables, state variables, elemental equations, continuity equations, compatibility equations, etc. It's all the same stuff. So don't be surprised by any of this stuff. It's all extremely similar to what you've been seeing. So this is the time when the heater is connected, and then this is the time when you disconnect the heater. And the prediction for each interval is discussed separately. So interval 2 is discussed here, and then interval 1 is discussed there. And then if you go back to your report requirements, it tells you what to plot and then give the final estimates of the time constant and R and C. So that is our lab exercise. It's pretty involved, and it does take some time. So try to be efficient with your time, but also recognize that there's no, excuse me, there's nothing that's too difficult at any point, but you just have to be careful to do the steps correctly all the way through. And if in the end you get temperature data that looks a little like this, it should look a lot like this. So if it looks weird, then something's wrong. Yeah, so you should know if you have it right in terms of your measurement. And the calibration stuff, you need to get that right. You can't come back and do the calibration later because the temperature could have changed. The ambient temperature could have changed. And so you do need to know what that is, that value, value of the temperature, the room temperature. I have it as TS here, which in the lab exercise description, I call it T infinity, the temperature of the ambient air, which is a common way to denote the temperature of the ambient air. So that is our lab exercise. You only have 1 week to do the report, so do please get on it quickly. I think it's fairly straightforward, so let the TAs know if you have any questions, and I'll see you guys in class.